I want to talk about phase estimation. Phase estimation is to quantum algorithms what a Swiss Army knife is to the rest of the world. It's amazing how you get to Shor's algorithm, you get to the middle of it, and phase estimation sort of comes in and solves all your problems. Or the HHL algorithm for solving linear equations, the first thing you do there is you use phase estimation. And I'm going to show you another application of phase estimation today to do yet another thing. And so it means that what I will do is that I will start with sort of setting up. I will go over Grover's algorithm. I think many of you know a lot about it, but I'm going to go over it to establish some sort of common way of talking about it. And then I will point out that there's something missing in Grover's algorithm. And then I will talk about phase estimation for a long time. And then at the end, I will show how phase estimation puts in the missing piece in Grover's algorithm. And so I will kind of go all the way back to talk about what is it that we're trying to do in quantum algorithms. And what I'm trying to do is the following. I'm going to just as a reminder say that when we do quantum circuits, we like to have sort of a wire or a line for every qubit, and the point is that the number of qubits is not so big, and what they represent is unit vector of size 2 to the n. And so it means that we are working with a really big unit vector. So now IBM has a quantum computer with more than 400 qubits, and so then it means that the state of that quantum computer is a vector of 2 to the more than 400 complex numbers. So it means more complex numbers than we have atoms in the known universe. Or maybe the Hubble, actually the Webb telescope may expand the known universe, and we have to upgrade this part of the lecture. But for what it's worth, a very big unit vector. And then the point of a quantum algorithm is to then do something interesting with those qubits in the following sense. What a quantum computer implements is a unitary matrix. And so it means that to a first approximation, we can think of as sort of right around here, we put an implementation of a unitary matrix. And so as you know, unitary matrix, U means that U dagger is equal to identity, and then dagger is the conjugate transpose of the matrix. And so this then also means that this is an inverse. So the inverse is the conjugate transpose of a unitary matrix. And now the point is that, of course, if we are working with n qubits, and I say that means we are working with a vector of size 2 to the n, it means that really this thing here is a 2 to the n by 2 to the n matrix. And so if we have to write down that matrix, that's like we already lost from the beginning. That's like way too big. The whole point of quantum computing is that we want an implementation of this matrix where the implementation of it, the way we describe it, I'm from computer science, it should be clear already. We always talk about implementation, but let's say we have a description of this matrix here that is polynomial in n, not exponential in n. And so that's pretty much the field of quantum algorithms right there, is which problems can we find where we can do something interesting for that problem. We can solve the problem with a description of a unitary matrix that's really small. And then there's this whole list of success stories with Shor's algorithm, Grover's algorithm, phase estimation, but many more. So then there will be a lecture this afternoon about quantum machine learning, and we'll continue with other algorithms. Of course, Hamiltonian simulation is the most famous one. And all of these cases are cases where the description of the unitary is small. And so the whole field of quantum algorithms is just like enumerating as many problems as we can where the unitary is small. And then we can do good stuff once quantum computers get really good. And so what I will do is, rather than continue this enumeration of algorithms, I want to dive in and to be very concrete about these two algorithms, Grover's algorithm and phase estimation, and say something about those. So with all this as introduction, I can now start to talk about Grover's algorithm. So what Grover's algorithm does is to solve I guess some people would like to say a database search problem. So it goes like this. So if we sort of say Grover's problem. Of course, this is named after Professor Grover. But the Grover's problem. So I want to write this in a sort of a very computer science style. So the input here is a function that I like to call f. And what this f does is that it takes bit strings of length n, because that's the same kind of n that we have over there, to bits. And so the way we can think about this is we have a database where these bit strings are the addresses, and then some of the stuff that's stored in the database is of interest to us, and we would like to find it. And so it means that the output is something like an x such that f of x is equal to 1. And the simplest case is that we have a database with just one thing of interest in there. And so it means the database, of course, has size, there's like 2 to the n possible bit strings. And then we are looking for this one thing. So we're looking for a needle in the haystack, a single needle in a very big haystack, an exponentially big haystack. And so if we're just using a classical computer, so before we start to think about the quantum side of this, what would we do? Well, there's absolutely no structure. This is why people like to say that Grover's algorithm is like unstructured search, or search in an unstructured haystack. And so what can you do? You cannot really do much else than just going through all of the bit strings and try f again and again, and then at some point, hopefully you find it. But you're going to spend, in the worst case, exponential many applications of f, 2 to the n applications of f before you get there. So this means that, so it's like classically, you're going to do like 2 to the n tries of f, sort of more or less 2 to the n. And then we want to beat that with quantum. And so, of course, one could say, what about probabilistic algorithms? So if you start to say, maybe we could do sort of a bunch of samples of x's and then try f on those, and then we could do math on it, and then we can work out that with reasonable probability, we can get something done. But it turns out that even here, probabilistic algorithms are not going to help that much. So that brings us then to the quantum solution, which is then Grover's algorithm. And the idea of the quantum solution is that we need to do square root of 2 to the n. Okay, so that's what it is, so bless you. Square root of 2 to the n tries of f. So this is why people say that Grover's algorithm is this quadratic speed up. So it's like there's this quadratic relationship between 2 to the n and square root of 2 to the n. And it turns out that this generalizes very nicely. If we look at what's actually going on here, then Grover's algorithm is like it's an instance of a much wider class of things one can do, and you can get this quadratic speed up in every case. And so what I will do is, because Grover's algorithm is so well known, I want to just talk about that. But once you generalize it, it's known as amplitude amplification. And so that's, if you ever hear people say that, oh, we can always get a quadratic speed up with quantum, no matter what. That's the secret. So there's something going on here that just is generally applicable. But I'll talk about this case. Okay, so I want to sort of be very mathy about this, and so this also means I write on the board because I want to slow myself down. And so you please ask questions. It's like we have the whole morning. I do have sort of, a pile of things I want to go through, but I can like speed up and slow down and, cover more or less of what I'm planning to say. I would much rather answer your questions. So I really welcome interruptions and things. And I can always say I don't want to take your question, right? So just ask, and then hopefully we can all build a shared understanding of this stuff. What I will do is that I will start to talk about Grover's algorithm in a sort of mathematical way, and then I will take a sort of time out at some point and sort of present it more like this in the beginning. But you should always just have in mind that it's all about building a small unitary matrix. That's really what we're trying to do. But let me just give some mathematical definitions here. So here comes Grover's algorithm. Okay, I already wrote Grover, so I'll just start over here. So we need a couple of helper functions. The first one I will call set f. So there's a reason why it's called set, but let's maybe get back to that. And so here comes the first part of sort of quantum notation here. That is a vector. I think you kind of all know this, but let me just talk for a little bit as if you didn't. So this is a vector. And so here these vectors are always this n qubit, sort of 2 to the n, so really big vector. And then when I write an x there, that's a way of saying I'm thinking about an n-bit pattern. And then maybe we just take a little bit of time somewhere to talk about what this means. So let's just write over here. So let's say that we had that n was equal to 2. And then, so what are the basis vectors here? So we get, just write some basis vectors on the board. Standard basis. So the way we're going to write these is then in Dirac notation, and the idea, at least the way I think about it, is that this is like position 1, and maybe we should think of it as 0, 1, 2, 3. So let's do it that way. So we call these positions 0, 1, 2, 3. Now we can write those numbers in binary. So it means that if we put these in between these Dirac brackets, then we get exactly the meaning here. So similarly, and the reason is that we have a 1 in the 0th position. So over here we write a 0. Here we have a 1 in the 1 position. So we write 1 in binary this way. And then we can continue the pattern. So here we have 0, 1, 2. We have a 1 in the 2 position. And then over here that should be 1, 1. So you can see this generalizes very nicely to any number, to any n. And so that's what I have in mind when I put an x here. And so in this case, what we want to do is that we want to take seriously that we have this function f that tells us where to find the interesting needle in the haystack. Maybe, of course, yeah, okay, so this is what f does. If f of x is equal to 1, that's the one that we really like. And so I'm going to do a trick, which is something one can spend a lot of time on, but today we are just going to sort of glance at it. What this thing does is that it looks at x, and then if that x is one of the good bit patterns, we'll put a minus in front of it. So you can see if f of x is equal to 0, nothing happens. Minus 1 to the 0 is 1, but otherwise you put a minus. So this is like a standard trick in quantum computing, is to use minus as a way to, in quantum algorithms, I want to say, to use minuses to mark things. And so that's what we're going to cook a lot of soup on. As a more or less special case of this, I'm going to also define set 0. And set 0 on x is going to be, so let me write it this way because I want to get back to it. We put an x if x is all zeros, and then nothing happens if x is not all zeros. You can see there's a close relationship. It's like 0 here is just like the case where f is marking the bit pattern that's all zeros with a 1. So for what it's worth, I'm going to use these two a lot. Now what I'll do is that I will take these two and then cook some soup on it, and then out comes Grover's algorithm, and then I'll be talking for a while about why it works. So to sort of put some math to it. But for now, let me make one sort of editorial comment on this. So we have the problem statement. The problem statement is really just given by this f, and then the place where f is going to play a role in the algorithm is here. So I'm going to build something out of this. And then there's this whole question about why is this unitary? Let's return to this a bit later. But we are actually building something unitary here. Actually, it's not so difficult to see now that I think about it. What is this set F as a matrix? Actually, let's just see it for set 0, and then it generalizes. What does this set 0 do? It puts a minus in this case here. So the vector that has a 1 and then a lot of zeros after that. What does it mean if we're going to put a minus in front of that vector? It means that we're looking at a matrix that in the top left corner has -1, and then it's 1 otherwise down the diagonal. So it's more or less the identity matrix, but it has a -1 in the top right corner. That is a unitary matrix, because if you multiply it by itself, you're going to get identity. The two minuses will cancel out, right? So this is clearly unitary, and this thing is then unitary as well, just by thinking a little harder. So we're doing well. So we're building unitary stuff. we'll have to come back to why we can implement this efficiently in terms of small unitary. But let me go on. So here comes the main thing to know about Grover's algorithm. So I'm going to call it G for Grover. So let me first write it. So we're going to use the Hadamard matrix and then apply to all the qubits. So I'm going to write tensor product n. And then set 0 is our fellow from over there. Then some more Hadamards here. Apply to all the n qubits, and then set f, which is then also our friend from the other board. Okay, just in case there's any doubt about this, let me say that Hadamard is a 2x2 unitary matrix that comes out to be like this, and it just comes up in quantum algorithms all the time. So we're going to use it here as well. Question?
Hi, I'm sorry if this is too basic, but can we please make maybe a super small example of how C0 and CF works so that I can figure?
Absolutely, absolutely. Good. So let's do. So let's just do C0 over here, and let's do continue with n equal to 2. So it means that this matrix here will be this. It's like I haven't gotten over that I want to write everything in the matrix. I think one could write a big 0.
Too many columns.
There are 5 columns. This is not going to end well. So let me try to be more organized this time. So I think I need to. Very good. So at least this shows people are not asleep yet. So we will go with this matrix here. Otherwise, yeah. Thank you. So let's see. So set 0. So now we are going to apply it to one of these things. So first we apply it to 0, 0, and so what are we going to get? So you can see that in this case that's exactly where we get a -1 here, and then we could also do set 0 on 0, 1, and then we can equally see that in this case we just get 0, 1 back. Right? So, okay, good. I'll do some more calculation a bit later, but it's good to get started with this. Anyways, we have to look at this in much more detail, but that's the very basic thing. And then now comes with this as the beginning. Okay, question?
Sorry, I've always wondered this. So if this minus sign in front of this unitary, it's a global phase. So why can't we just...
It's just because it makes my calculation nicer. We don't need it. We don't need it. It's just like I want to end up with something that's +1 at the end instead of -1. So I just love to do this. It's just me. There's nothing about you. I mean, if you don't like it, that's blame me, not Grover. Right? That's okay. So now comes what's going to happen in Grover's algorithm is already said over here. We're going to do square root of 2 to the n tries of f. And the way this is going to happen is we're going to iterate the application of this G in a particular way. And I'm going to spell this out just to be absolutely clear on what it means. But really it's just like for loop, iterate G square root of 2 to the n times. And so it goes like this. So let's say that we have X is just my description of our n qubits. And initially it is this. So all qubits are initialized to ket 0, I guess we could say. And then what we're going to do is the following. We're going to do 3 steps. In the first steps, we will apply Hadamard to all the qubits. So we apply Hadamard to all these x's. What this does is that it puts all the qubits into a uniform superposition. So it means that now there's an equal probability of measuring any bit pattern at all in here. And then we will do our for loop. I'm going to write it as repeat just to make it very clear that we are repeating something. And what we will do here is that we will apply G to X. And we will do that square root of 2 to the n times. So I'm going to write it as approximately square root of 2 to the n times, just to be not too hung up on it, but we'll get back to this point. So this is going to play a big role all the way to the end of the lecture about exactly how many times are we going to do this. But we will get back to that. And then, yeah. It's a computer science applied. Yeah, exactly. Very good. So it's like, if we think about this circuit here, really what I'm saying is there's going to be a bunch of Hadamards here, and then all the qubits have changed state, and we keep applying matrices after that. Thank you. Yes. Yep, this computer science undercurrent is going to be there all morning. And then at the end, we want to output a bit pattern so that we get this bit pattern such as f of x, that bit pattern is 1. And so it means that here we measure x, and then we're done. And now comes sort of truth to be told. What will be clear as we go along is that it is a probabilistic algorithm in the sense that sometimes you get the output or n output that you want with probability 1, but nobody says it's going to be 1. And it'll be much clearer as we go along why it's not always. So there's some probability you don't get an x. Of course, you can check it, right? You get a bit pattern here, and then you can just check it and see if f of that bit pattern is 1. And if it isn't, you run the algorithm again. So that happens a lot in quantum algorithms, that you try something, it didn't work, and you try it again. And that's I guess one can say there's a lot of probabilistic algorithms going on in math and computer science, and so there's always this thing about probabilities of something. In this case here, it's very concretely, there's a probability you get the right result, and you can check it, and if it isn't the right one, then you try again. And so in practice, you may have to run quantum algorithms many times to get the right result. But we will definitely go into this more. So in the spirit of this board over here, I think I'll take some time just to go over what this looks like if we do an example. So I'm just going to take like a sort of a calculation break and just show something. So let's see how much I can get done on this board here. So let's take an example. Let's in the spirit of that over there, we'll continue with n equal to 2, and let's say that f of sort of most of the bit patterns is 0. And then we have the one that we are looking for, f of 1, 1 is equal to 1. So this means that if we plug this into Grover's problem, that's our f, and what we are hoping is that we get an output x, which is actually 1, 1, right? That's the one case where f of 1, 1 is 1. So really, that's all I'm going to do. I'm going to just walk through this and see that when I measure x, am I going to get 1, 1? And what is the probability that I'm going to get 1, 1, right? So I think many of you would be able to do this easily, but just watch me do it. So, and ask questions on the way. So as a little bit of a warm-up, there's one piece of computation that's going to happen a couple of times. I'm just going to show you. So, okay, so now we're doing Hadamard twice. So let's just look at the following state. So we have a linear combination of 4 things, and there's a minus. Here's the minus. And so let's just look at what this is, right? So it's just like continuing the examples from over there, and this will then be important when we walk through Grover's algorithm on the example. So let me try to do this sort of the long-winded way. Applying Hadamard twice. Okay, so we have Hadamard over here. So of course, maybe I should say that now we can very concretely say that when I write this notation here, it very literally means a tensor product of this matrix with itself. Okay, you cannot see anything, right? So maybe I move this a little bit. No, I should not do this. Do not move the lectern. There's actually a sign on the floor that says, do not move the lectern. I don't know whether it was visible before, but it is now. Okay, I'm not moving it. So anyway, this thing is really Hadamard. Oh, really? Oh, it slides. I had no idea. I've come here a bunch of times. I've never seen anyone slide this board. So you learn every day. Okay, so let's just look at what this is. So I wanted to point to Hadamard and say that there's a 1 divided by square root of 2. And then, of course, when we are going to apply a tensor product of 2 of these, we end up with a factor of that thing multiplied by itself, so that's going to be a half. So there's going to be a half somewhere in this. And then we're going to apply this sort of linear algebra style to each of these, and so we're going to get a big half out in front. And that's, so now there's going to be a lot of work after that. So what is it Hadamard does? So of course, you can just sort of do math in your mind. You can see that it puts a minus somewhere. So let me write what it actually is. When we focus on this thing here, we get 0, 0 plus 0, 1 plus 1, 0 plus, I'm going to be a bit more parsimonious with the space, otherwise this will not work. So one more time. 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. So that's actually correct. This is sort of one of these things where you can check that this is true, and the way it kind of comes out is that if you, for a moment, don't do anything with this 0, then this 0 over here kind of gets mapped to a 0 and a 1, and we get something out here. And then we can also say, let's take the case where this 0 here, of course, gets mapped to a 0 and a 1. We can take the case where it becomes a 1, and then this one still gets mapped to a 0 and a 1. Okay, so this like hand-waving through multiplying some 4x4 matrices, but you can easily check that this is true. Now all we need to do is then to start to get these pluses and minuses right. And so every time there's a 1 here, it's a sign that there's probably a minus coming. And then here we have a minus and 2 1s, so there's going to be a whole lot of minus, minus, minus to manage this stuff. So what I will do is that I will write this out as, actually, just like this, and there should be a minus. Thank you. Haha. Okay, so maybe I put another arrow here just to say, yep, there's the minus. Okay, so let me just show you how this works out. So, so this 1 is going to get us some minuses here and there, and it turns out that if you think carefully, they show up here. And then, so then here we have the 1 on the other side, so now we get the minuses in some different places. So here it turns out that it becomes like that. And then, so the last one will just keep the minus there, and then we will do these. And so in this case here, the minuses show up here instead. So you can see they show up sort of interesting places. And at the very end, we get a plus because there were 2 1s up here, so now the 2 minuses cancel out, and we end up with a minus there. So it looks about right? So it can be checked. Okay, so the thing that I want to get to is that now we can simplify all of this. And so let's just see how many zeros that we have. So here we have 1, 2, 3, and then minus 1, so that would be 2, right? So 2 0 zeros, and hopefully plus. Let's see, so we have 1 0 1, minus 1, so that's, and then plus 1, and then minus minus, so we end up with 2 of those as well. So 2 0 1s. Then we do 1 0, so we have 1 of those. That's 2, and then we do minus, now we're down to 1, and then minus minus, now we have 2. So 2 1 zeros as well, and then finally the plus 1s, we have 1, minus 1, okay? Then another minus 1, now we are negative 1, and then over here we have minus plus, so now we're down to minus 2. So here it ends up with minus 2, 1, 1. Okay, so we can simplify this a little bit. So I just want to have this simplified thing sitting at the end. So all the half and 2s cancel out, and we are actually down to where we started. So if we look carefully, that's exactly the thing that we had at the beginning. So Hadamard applied twice to this thing gives us that thing back. Okay, so that's sort of a little bit of calculation. So I will show a bit more calculation today here and there, but it's just like good to see how this notation works. Now I will carry through this example. So this means that I will apply these steps to this case of f. And so it goes as follows. So we go over here, and we see what are we supposed to do. We're supposed to first set up a bunch, well, 2 qubits to be precise, that are both 0, so it's ket 0, 0. Then we are going to apply Hadamard to both of them. Then we are going to repeat this some number of times. And I'm just going to tell you right now it's one time is the correct answer. That's why n equal to 2 is such a good example. But we will return to this case of what it is in more general. But this whole thing is just one time. And then finally we will measure and we see what we get. So here comes the calculation. So I'm just going to write it as we have ket 0, 0. Then we apply Hadamard to both of these. And then we apply G once. Just write it like that, and then I'm not going to write measurement because then I'll just have to repeat it many, many times. So I'll just start working on this. Maybe I take advantage of the width of the board. Okay, so so we already know sort of Hadamard applied to 0, 0. We can just copy, that was this case down here. So we get G and then a half, and then 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Okay, so then now we're going to do G. So for a moment, I'm going to write G out so let's see, so what is G? So we have this minus, we have this half can stay. So let's just write it as G, and then we have minus 2 Hadamards, set 0, 2 more Hadamards, and then set F, and then comes a half, and then the story up there. Okay. All right, so now we're going to do set F. What is set F going to do? Set F is going to say, for the bit pattern that you really like, we're going to put a minus. And we know that the bit pattern we like is 1, 1. Right, so 1, 1 is going to get a minus. So I'll just keep writing here. So we have to duplicate a little bit, but that's how it goes. So set 0, Hadamard twice. Set F is then, so we get a half, and then we just get a minus in the right spot. So let's do that. Minus. There's the minus. 1, 1. Okay. Hadamard applied twice too. That's the thing I just labored on over there. So we know that Hadamard applied to this thing does nothing. So I can just do that. So to have a clean slate for starting to talk about the next case here, I'm going to actually write out where this Hadamard is gone. And then let's think about this case. Okay, so what does set 0 do? Set 0, what it does is that it puts a minus in the case where the bit string is all 0. So in this case, 0, 0. So well, there it is, right? So it means that we just put a minus there, so we get minus. We kind of making our way to the end, minus 0, 0 plus 0, 1 plus 1, 0 minus 1, 1. Okay, and then we're going to do Hadamard on that. I want to take advantage of that I've already done this. So what I will do is that I will say right around here, I'm going to say let me get into that situation over there by by subtracting 2 of these and then adding 2 of these. So let me just do that, because now you can see that now this, once we sort of group like this, then now we have 1, 0, 0 plus plus minus, right? That's what I had over there. And then this 0, 0 will just happen separately using linear algebra here. So we get this, we still have a half. Let me just be careful about that. And then we have to do Hadamard on minus 2, 0, 0. So that's going to be minus, and then of course, this 2 that's sitting there is going to cancel out with the half that we get from the 2 Hadamards. So we can just do 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. And then plus, and then we know that this whole thing gets repeated. So here we have minus 0, 0 plus 0, 1 plus 1, 0 minus. That's not true. There should be a plus here. Plus, I just set up everything so there should be a plus here.
There's no Hadamard in the beginning, right? Just apply there.
Oh, so I just applied it? Yeah, thank you. I don't know why I wrote this again. Too much excitement. But the minus is still there. Thank you. Very good. Okay, so we have this, and I think that I'm at the point where I will just like...
And the minus is...
Yeah, so that's a very good point. So there's something about these factors of 2 that we need to get under control for a moment here. So let me do that. So so let's just go through this. So I want this minus to just be, totally global. Yeah. It should be totally global. Very good. Absolutely. So we get Hadamard applied to, so we have the half. Yeah. See, that's what you get when doing these tricks, right? Then it becomes difficult to see. You know what? I want to write this line one more time, and then we will get these things right. So let's just do this a little bit more. Yes, let's just do this exactly. Let's just do a big minus and a half outside. I very much agree. And then here we can just do minus 2 and a half, and then we can sort of get it right that now we can do Hadamard on 0, 0. And then we can do our friend over there, which has so we have the half is global, and then this thing now just becomes same thing, no change. Now I think we have it right. Minus 1, 1. Okay, thank you. And then the big global parenthesis instant. Okay, good. All right. So then what do we get? So here we these two cross out. And then, so let's see what else we have. So in terms of 0, 0s, right? So we have a minus 0, 0 and a plus 0, 0. They're going to cancel out. So here we have a minus 0, 1. It cancels out with a plus 0, 1. Plus 0, 1 cancel. Well, it's a minus 0, 1. Cancels out with a plus 0, 1. And then finally here we have a minus 1, 1 and a minus 1, 1. So we get 2 of those. And of course, here we have minus and a half, so we end up with this. That's where the minus is there. I wanted that minus to cancel out with that minus, right? So what does this mean? So we did the calculation. We have this thing here. Now we can measure. I'm going to sort of just hand wave my way through measurement today. But what it means is that we get some bits out. And in this case, there's only one thing to do. We get some bits out of this thing. And so we're going to get 1, 1 with probability 1. And so that means we succeeded. So we actually got a bit pattern 1, 1 for which f of x is equal to 1. So this is just good. Okay, so that was the example. Any questions about the example? You didn't ask many questions, probably because you're very well informed. And so I think now you know that I know some of what you knew already. And so, question? Yeah, there's some kind of diffusion going on. So if one wants to explain it that way, absolutely yes. Yeah. Okay, so now let me. Yeah, so let me comment on this. So very good. That's an excellent lead-in. So let me say something about this. So
I had a question.
Oh yeah.
So ZF is a reflection, and Z0 is a reflection.
It is
as well.
It is.
And the H's on the sides of Z0 means it's a conjugation. Can I think of H, Z0, H as another reflection, or?
I think you can.
Reflection
H
about
is not
the
a unitary, right? So it's not.
H is.
H is unitary. It certainly is. It certainly is. Yeah.
Is it like reflection about?
Yeah.
The orthogonal plane of the uniform?
Yeah. Some people like to explain the algorithm this way. So the intuition is right. So both of you definitely right. Okay, so let me now comment on this question about that we want a small unitary that to come out of this. So I'm going to delete this calculation and then show how to implement a circuit that does this. And
Sorry, can I ask you another question just as you were raising this?
Yeah.
You have applied ZF 4 times, right? I mean, you have in computing your ZF, you have applied F 4 times, right?
Of course, this is the thing about quantum computing is that because it does linear algebra, it will apply f on the superposition of these. So it feels like it's applying it once. So that's like at the very heart of how quantum computing works. Is you establish a superposition and use it. Count that as one. Yeah. Otherwise, this whole field is sunk right now. So let me give a circuit that does this. So we have our two qubits. They're both going to be 0 to begin with, and what are we going to do here? So we just follow what the algorithm is saying. We're going to do a Hadamard on both of them. So we'll put a Hadamard here. And then the next thing we're going to do is we're going to apply G, which means the first thing we have, now I'm really going to ignore this minus. ZF, what are we going to do with ZF? So ZF is saying, for the example, that we're going to put a minus for the bit pattern where it's 1, 1. So the way this comes out in quantum circuits is as follows. So we can do a control on this qubit and a control on this qubit, and then actually, so let me do it this way. So we'll put in a helper qubit. So this is our helper qubit. I don't know why I'm walking around with this piece of paper. So we have a helper qubit here, and then what we do now is that we say if both of these qubits are 1, so that's the good case, we are going to do an X down here. And so what this means is, very concretely, we're going to flip this 0 to 1 in the good case, right? So then what happens if we have a 1? Well, if this has been flipped to 1, this helper qubit, that's the case where we want to put a minus. And so how do we put a minus? That's the set gate. Okay, so here's another case. Set is this matrix here. So you can see this is the one where if we are giving it the ket1 vector, we put a minus. If we give it the ket0 vector, we do nothing, right? And then the right thing to do is to do what's normally called uncompute. So we have to just make sure that nothing is untouched. So this is the right thing to do. But we got our minus. So that's good. And then we go back to the algorithm. The algorithm says we did this. Now we should do some more Hadamards. And then after that, we should do a set 0. Okay, set 0 is a lot like, so we can say that this thing here, that's where we do set F, right? Now comes another part where we are going to do set 0. And so all we do is we change the controls so that instead we are testing on whether these two qubits are both 0. That's usually written this way. And when we do X. And then again, we can put a set for the good case, and then we uncompute. So we get this. So here we have set 0, and then the algorithm is saying, and at the end, Hadamard again. Here we are. And then what the quantum people like to do is to say, and then we measure these two, and out comes the bit pattern that we want. And so just to be sure, I got up early this morning and typed this into an online quantum simulator, and it gives exactly what I got in the calculation that was just erased. So it actually works. So I will skip bringing my laptop and showing you that is actually true. So what do we know about this? So first of all, we are just working on 2 qubits instead of a vector of size 2 to the 2, which we do need a helper qubit, but in practice not so many. The number of helper qubits for, if we generalize this to n, is about n. So it's like you have n main qubits from the problem, and then another n helper qubits, and then you can do what you want to do. And then what we have here is then sort of seems to me very clearly polynomial in the size of n. And then what we need to do is then to get the physics people to be able to repeat this body. So it's like, you have the quantum computer, there's a program that says do this, and then they just need to be able to put a loop around it and then execute this a bunch of times. And then we still have a polynomial description of the unitary this way. So anyway, so that's the circuit.
So in the absence of noise, everything here up until measurement is deterministic. It's linear algebra.
It's just linear algebra, absolutely. So a lot of the sort of the non-deterministic stuff in quantum comes from the measurement. And so in this case here, I'm just arranging myself so that down there it's erased is something that happens with probability 1. But a lot of the time it's not true. And then that's where you need to repeat. And then oftentimes what you have to do is to repeat a lot. I still remember when I first talked to the Google people, they say they usually repeat 10 million times, build a bar diagram, and then they see where the big bar is, and that's the one. Right? So, yeah.
Maybe you'll tell me you don't want to take my question, but you have the helper qubit, right, that introduces some randomness at this point in time, right?
It does, but what we are doing here is that we are seeing to that it gets changed back to 0. So it doesn't really introduce randomness. So this is why I'm very careful with doing this.
And the other question is, so here you've coded your F into your pattern, right?
Yep.
So if your
Yep.
F is very complicated,
Yep.
then
It could be very big.
it could be very big.
Exactly. So this is exactly where the water divides, is that some problems are not going to be solvable with a polynomial time quantum circuit, and other ones will. And the whole field is to sort out which one is which one, right? In the same way, you could say that the field of computer science is sorting out which problems can be solved on a classical computer and which ones can't. That's the decidability question. So here it's just everything is moved like one floor down, in my view. Okay, so now I want to talk about why this works. Okay, but please ask questions.
So you don't need that H for the helper qubit, right? At the end, you don't need that H for the helper qubit.
Oh, that's a good point. That's a mistake.
And
Yeah, that's right. Okay, thank you.
CF is just a controlled Z gate, right?
It is. So this can most likely be condensed into something smaller. So I'm doing it this way because, for a very particular reason, when I learned Grover's algorithm, I had implemented my own quantum simulator that takes input in Jens style. And so my program for Grover, written in ASCII, actually looks like this. And so this is what I remember. It's boiled into my brain at this point. But you're absolutely right that there are other ways of cooking this up.
Yeah, and I'm quite maybe stupid, but you need to know the solution to construct ZF.
Right. Yes. So that is sort of a general complaint about these early quantum algorithms that it's like you. It seems like you already know where you want to go before you start. The way I think about this, for better or for worse, is that you should think of it as that somebody handed you this ZF circuit. And so now you no longer know what it is. You just have this circuit. And if it's a very big, there's no way you could just like inspect it and say, oh, now I know what the answer is. The only way you find out what the answer is to build this together. And now you know, right? So that's like, I don't know how compelling this is, but that's how the whole field wants you to think about this kind of problem. Okay, other questions?
Is there a generalization of this to have a function that's like sort of a landscape, you're trying to minimize it?
Yeah, absolutely. So this totally generalizes to any, so let me say a word about this generalization. So the idea here is that in this whole picture, it turns out that the key fellow is actually here. It's this very innocent looking step. So what this does, of course, it puts the qubits into a uniform superposition. Everything has the same probability of being something, and then the rest of it happens. This can be generalized. We can put in any unitary here, and the whole story works the same. And so what it means is, if we short circuit, is that for any unitary that's really, you can just think of it as a description of a probability distribution over 2 to the n cases, we can get a quadratic speed up in how to work with it. Yeah, but it's also, yes, that is also true. Okay. Okay, so
So you can, in general, just test ZF with all inputs? I mean, here you're doing it for a specific
you
case.
really can't, because if n is 400, you're not going to test it on 2 to the 400 inputs.
That's the problem.
That's the problem, right? So that's why the field has a future, that we can't do that. Okay, so now what I want to do is to give a sense. There's a question, yes.
Can you comment on the relation between this quantum algorithm and the classical parallel computation? When it proves that we apply the ZF on all superposition.
Yeah. So I claim that in terms of how I understand classical parallelism, the only parallelism we are getting here is like here we have like a couple of things happening at the same time. But this thing of operating in parallel on a superposition, the problem there is that classically, just to construct the superposition, we already need exponentially many resources, right? So it means that even if we could operate in parallel, we would need, first of all, exponentially much storage, and then an exponentially big number of cores, right? So it's just like, it's not parallelism in the normal sense. So that's kind of the contribution of quantum, is that you can just have nature take care of an exponentially big superposition and do stuff with it. Where classically it's like, yeah, we need exponentially amount of stuff here to do anything. And, yeah. Question?
Is this F fast to compute?
One more time?
Is this F fast to compute?
Yeah, let's just assume it is. Yeah, so for better or for worse, I kind of swept that under the carpet. Let's assume it's just like super fast. So. Okay, let me, okay, it's a nice diagram, but I'm going to erase it. I want to say something about why this works. And I'd much rather work with the mathematical description than with anything else. So now these, all this stuff goes away. And so it turns out that there's some kind of the following thing going on. I'm going to put it up here high enough that everybody can see. There's something like this going on under the hood here. There's sort of a circle, and at some point there's going to be a vector here, and then there's going to be something about moving that vector that way. And what I'm going to do now is I'm going to make sense out of this picture. This is actually what's going on, but it'll take some steps to get there. So what I will do is that I'm certainly talking about the general case where there could be any number of bit strings for which f of bit string is equal to 1. And so I'm just going to talk about this general case. And I'm now going to define an A and a B. So in computer science, they have the mnemonic that the first thing here is, so what is it? It's a set of bit strings, and bit strings of length n. And these are A for awesome. These are the good bit strings, so f of x is equal to 1. And then the other ones, that's the bad bit strings. So that's the one where f of x is equal to 0. And what we're going to do now is to actually, let me just introduce, I need very little notation to get this done. So let me introduce all the notation. So somewhere I'm going to get tired of writing 2 to the little n, so I'm going to call that big N. And then I'm going to define that little a is the number of elements in big A. And little b is the number of elements in big B. So I think you can see that this n here is equal to a plus b. And now what I will do is that I will define a ket A and a ket B, which is then going to be built out of the vectors in A and B. And so it's just going to be the sum of all the vectors. So let me use a bit of space on that. So all vectors in A, ket x, and then we have to normalize, so 1 divided by square root of A, because we do want a unit vector, right? So we just make sure that it's a unit vector, and then B is then for the other one. So there's a normalization constant, all the x's in B, and then ket x. Okay, so those two are going to be very important. First of all, they are unit vectors because I normalized them, and also they are orthogonal. So why are they orthogonal? Yeah, so it's two completely disjoint set. This is just a whole bunch of basis vectors, right? As the stuff that I erased. And so it's just a bunch of, there's just like no basis vectors overlapping. So they are orthogonal. And indeed, this orthogonal thing is going to show up over here, because at some point I'm going to put this thing here as a vector over there, and I'm going to put A over there. And so you'll see why this makes sense. So right now, this is just like two vectors that are orthogonal, right? But at least it makes sense that there should be a right angle there. That much I can say. So we will work on it some more. So the thing that is, let's say the surprise of Grover's algorithm, the inside of Grover's algorithm, is that the following thing is true. If I take this G that defines the body of Grover's algorithm, then the following is actually true. Maybe I should write lemma just to make it look very official. So here comes G applied to A. What is that? So if one works hard enough, one can show that this is equal to, and then comes a calculation that I was thinking I would skip. If for some reason at some point people really want to see it, I'll be very happy to show it. But it comes out as follows. So what do you see? You see that if you start with this vector here, you're going to get something in the span of A and B. And then immediately we have to ask what happens then if we do B. And then it turns out that it's very much similar story. We get something in the span of A and B. So now you can see why I'm writing a two-dimensional space. Because really what's happening is that the body of Grover's algorithm is just moving us around in this two-dimensional space spanned by A and B. Then we can talk about exactly how does it move around. But really, to a first approximation, this is the initial vector. So this vector here is Hadamard n times applied to 0n. And then something happens. This is what this arrow is supposed to say. Something happens that you keep moving around. And so the question is, what happens? So I already did one calculation today. I think this is enough. So I'm going to just say that this is true. And then I will talk about what exactly it is that's going on here. So let's organize this a little bit differently. Let's organize it as... I think I can squeeze this in down here. Let me squeeze in something here. So let's be serious about that it's a two-dimensional space, which means that we should really just be thinking about a 2x2 matrix that then does this operation. Let's just see what it looks like. I'm going to call it M. And so there's going to be 2x2, and it's just going to be quite big. So actually, I'm going to put in some helpful stuff so that we can see where we are going with this. So the idea is that up here we have like the from space, and down here we have the to space. And then, of course, right, this is how it works. And then I'm going to have, B is like here and A is there. I guess I should write it as ket. Okay, whatever. I'm just going to write B and A, and then B and A. So you can see I'm putting B in the first column and the first row, and A goes to the second column and the second row. And now we can organize this stuff. So I'll just take a moment to actually write this out, and you will see what comes out of it. So if we do B to B, then here we'll have to do something like minus 1 minus something or other there. And if we are going from B to A, then we get 2 square root of something divided by n. And then if we are going from A to A, just a second, from A to B should be the first one up there, we get minus 2 square root of AB divided by n. And then finally, A to A, that's this 1 minus, yep, it is good. Okay. So there's just one thing that bothers me about this. Let me, Just think about this, which, oh, I know what's going on. Okay, so the thing that bothers me is that there's a little bit of more math that needs to be done, because you can see these two off the diagonal, they look very similar with a minus. These two look a little bit different, but it turns out they're not so different after all, because here we have an A and here we have a B. And n is A plus B, exactly. So it means that those two fellows are actually equal. So it takes a little bit more. We can do the calculation if you like, but these two are actually equal. So what does this mean? It means that this looks an awful lot like a rotation matrix. And I'm going to hammer this home this point by saying, let me define, I'm going to look at square root of an, and I'm going to look at square root of b divided by n there. And so what do we know about these two? So we know that if we take the square and add them up, we're going to get 1, right? We take the square root goes away, and then a plus b is equal to n, so we get 1. So this means that we should be able to find a theta such that sine of theta is equal to this fellow, and cosine of theta is equal to this fellow. So that should be eminently doable, so we'll do that. And then I'm going to observe that if we then organize a rotation matrix, which I could just, I like to call these, I'm going to continue over here. If we organize a rotation matrix so that what is the traditional way? Cosine of theta, and then So there's a minus somewhere. Here, up here is minus sine of theta and sine of theta. So if we then start looking, it turns out that there is a very close relationship now between, so we can kind of see it, that these things here, they are very closely related to these, and then one can do math on it for 5 minutes. It's 2, exactly. Very good. So I will just write it as, if you do 2 of these, you get this. Right? So a little bit of math will show that this is true. It's just like one line of calculation, but it's like I already had enough trouble with calculation this morning, so I'll stop here. So what does that mean? It means that what we do when we run the body of Grover's algorithm is we are really just rotating by theta twice. That's all we're doing. And we know exactly what theta is. We can kind of, we know, well, we don't know A, right? That's the problem. So for a moment, that's the big point that I want to get to. We don't know A, but if we knew A, we would know theta, and then all of this would work out beautifully. But for a moment, let me just hammer home the point about what is it then that Grover's algorithm does. Here, we are going to do a rotation by 2 theta. And then we're going to keep rotating. And the whole objective here is to keep rotating onto a point where our vector, the state of the quantum computer, is as close as we can humanly get to this A, right? And that A is, of course, exactly where we have all the good guys. And at that point, we will measure. And then chances are that all the ones that where f of bit pattern is equal to 1, we're going to get one of those when we measure. There may be some other ones because, we may have a vector that's like off by a little bit, and then it's not totally going to work, but it's going to work a lot. So what does that mean? It means that the only problem we have left is how many times should we rotate? So over here it's written like, yes, like some number, but now we want to be very accurate because now we know that we really want to stop at the point when we hit the y-axis or hit it very close. And so I want to now end the Grover presentation by saying we can do a little bit of math on this, and which I will do here. So yeah, this is going to be interesting for you at some point. So let's go back and see where we are at. So where are we when we have done this? So this Hadamard once, right?
For large n, your theta is like root A over n.
It is, yes. That's exactly this. That's exactly what this is. So. Yeah, we don't. That's all we need. There's not going to be any more. All the reflections were as sort of a little bit touched upon earlier as kind of built in here. There's not going to be any further discussion of reflections here. It's just rotating. It's really just rotating. Nothing is swept under the carpet. So what I want to say is, let's look at the state. After we have done the initialization. That's what I call step 1 here. So we apply Hadamard to all zeros. So what is it that we get at that point? So if we look at our definitions of everything, we have gotten the following: cosine theta, and then b, and then plus sine of theta a. It's not a very good B. So that's just bringing in the sines and the cosines that we had before. So again, this yeah, we can go through more calculations. I'm looking at my lecture notes, so I have the calculations here, but it's like I want to do fewer calculations and more big points. So we are at this point here. The point that I do want to explain in detail is, how can we now understand the rotation with 2 thetas at the time? So let's say that we're going to do k iterations. So here we say this thing here. Let's just say that we're going to do k, so be very precise. And so what does that mean? It means that as we are rotating, then this angle that we are rotating with, so maybe I can say after, so initially we have this, after initialization, and then after k rotations, as we can now say, after k applications of the body, what do we have? So now we are going to do cosine of not a single theta, but 2k thetas, well, plus the one that we had already. So we get something like this, right? B, and then plus, and then sine, and then again we have 2k thetas plus 1, and then A. Okay, so that should be the state after we have rotated k times. So just adding 2k thetas along the way. Now we want to measure, or rather we want to know k, right? This is the whole point. We want to know k. When is it that we have this very close to the y-axis? And so what does that mean? It means that we really would love for this fellow here to be 1, right? So if sine of something is 1, that means we are up at the y-axis. And so when is this thing 1? So we can say that's sort of roughly, so we want that this thing up there is 1. Okay, so what does that mean? It means that we should be interested in that sine of 2k plus 1 theta is equal to 1, which is sort of roughly 2k plus 1 theta should be equal to, so okay, sine inverse of this, that should be about pi divided by 2. And then we can do more math on it, and out will come that k is going to be, roughly speaking, not putting too fine a point to it, pi divided by 4 theta minus a half. Okay, so then that's a couple of steps of calculation there. Okay, great. So do we know theta? No, because if to know theta, we need to know A, right? So to short circuit all of this, let's just go with A equal to 1. So we're just looking in the database where there's only one thing in there, and we know there's 1. So if there's 1, so what does that mean? So it means that sine of theta should now be equal to 1 divided by a really small number, 1 divided by 2 to the n. And then if one does math on it long enough, out will come that if A is equal to 1, then k is equal to 1. Right? So that's just how it comes out. That's why I picked this example, because I knew I could just apply Grover's algorithm. And then the thing that's missing in Grover's algorithm is, what if we don't know A at all, right? Okay, maybe there's nothing in the database, but we don't know how many good ones are in there. There's probably not very many, because if it was a lot, we would not use a quantum algorithm. If there was lots of good ones in there, we would just use a classical probabilistic algorithm and just try a few until we find one. But if there are not very many, and we don't know how many, then you can see it's a disaster. We may totally over-rotate or totally under-rotate, right? We have no idea whether we will ever be close. And so that's the missing piece in Grover's algorithm. If we don't know, then what do we do? And so this is where phase estimation comes in, or rather it comes in after the break. So we'd like to take a break for like however many minutes the organizers like to have a break. And then we come back. Okay, but I'll take some questions before the break. Question? So I'm going to do a trick, which one can then verify works out. So the idea is to go back to the definition here and then say theta, of course, should be sine inverse of 1 divided by 1, right? 1 divided by square root of n, because we're doing k equal to 1. And then what I'm saying is that this is a super small number. So this sine inverse, it's roughly speaking just this, which is kind of what you said before. And then we can say, what is k then? So k is going to be, well, it's going to be this, right? So now we just continue here. So then we get pi divided by 4, and then we're just going to take this on faith, so 1 divided by square root of n minus a half, which is not going to play. Absolutely. So here we get pi, but I see. Okay, I'm sorry. I still had in my mind the example of n equals to 2. Okay, so now we have the bug finding in real time. For n equal to 2, it's 1. I was still working on my example, of course. Now we do the general. Good, so we do the general case and we get it right. So here we get, there's a kind of a square root of n somewhere there, right? Minus a half. Nobody cares about this minus a half anymore. So, but as you can see, if n is equal to, what is the n? if little n was equal to 2 and then n equal to 4, then we get something like a bunch of things cancel out, and then pi minus a half, pi divided by 4, whatever it is. So before you know it, if n was equal to 2 and a was equal to 1, then this is right around k equals to 1. But however, of course, that basically this is like square root of n. And then we are back to what I said. So the general case is very much this, as you're pointing out, and then for a very little n, and then you can be lucky that it's just 1. Okay, good. So I think we have established this, which is fine, and it's going to be this in general. The problem is that the constant matters. How many times are we exactly going to rotate to make this work if we don't know how much is in the database? This is where we bring in phase estimation. Okay, now I think there's a break. So how long do we have break for?
15 minutes.
15 minutes. Okay, so now I'm going to present the Swiss Army knife of quantum algorithms, which is phase estimation. And to a first approximation, what phase estimation does is to find an eigenvalue if you have an eigenvector already. So really, you have a unitary matrix, you have an eigenvector, and then you run phase estimation, and you get kind of an eigenvalue. Okay, so I will be more precise about what really is going on. It turns out this is extremely useful. And it turns out that as useful as it is, actually the algorithm that I will present satisfies something even more general, which is that if you are given a linear combination of eigenvectors, then what phase estimation will give you is one of the eigenvalues that's connected to one of those vectors, which is incredibly useful, as you will see. And the way I will show a use that's very easy, so it can be done very quickly at the end of the lecture, is that I'm going to find theta. And if we know theta, then we know we can work out k, and we can iterate the right number of times, right? So what I will do is write something on the board so we can see the definition of the problem. And then I will talk about that underneath phase estimation is the quantum Fourier transform, which is like the best thing since sliced bread in quantum computing, because the quantum Fourier transform is exponentially faster than the classical Fourier transform. And so in a way, if we should just talk about what is really, really smart in quantum computing, we could give sort of the whole lecture about the quantum Fourier transform. But what I want to do is instead to talk about what I think is sort of the packaging of the quantum Fourier transform, which to me is phase estimation. Phase estimation is this thing that is at a level of abstraction that you can apply again and again to all kinds of problems. And then all we need to know is that underneath is quantum Fourier transform, and it's really smart. So that's how I will go about it. So I will touch on the quantum Fourier transform. I just don't want to say as much as I would if this was sort of a normal lecture in computer science where I have much more time than I have today. I want to focus on other things. So here comes the phase estimation problem. I really think that this thing with phase estimation, it's to me, it's like, come on, could we just call it find an eigenvalue or find information about an eigenvalue? But okay, it's called phase estimation. Question?
So you mentioned the quantum Fourier transform is faster than the classical one. Is this a rigorous statement, or just people cannot find a better classical algorithm?
Yeah, I think it's not a rigorous statement. I think as far as we know, it's okay. The rigorous statement is it's exponentially faster than any classical algorithm that we do know, and that's as far as we have gotten with this. So you know, I'm sure it'll come up in the lecture this afternoon that there are sort of various quantum machine learning algorithms where people thought that the quantum machine learning had an exponential leg up on classical machine learning. And then it turns out the classical machine learning people improve their algorithms, and then there's not as much of a leg up anymore. And quantum Fourier transform is one of the places where there's still an exponential advantage over anything that's known, right? So, and of course, the best algorithm for the classical Fourier transform has stood since the 60s or something. So it's like we're not waiting for improvements on that front anytime soon. Okay, so here comes phase estimation. So the input is I'll just write it in very brief notation, a unitary U, and then an eigenvector of U. So an eigenvector, I'll write it as ket psi of U. So this means that U applied to ket psi is equal to something here. So the question is, so of course we're going to get some kind of eigenvalue here. That eigenvalue, I'm going to write it as e to the 2 pi I theta. So that's clearly some kind of complex number going on there, right? The eigenvalue is going to be a complex number, and I just prefer to write it like this. So if you know any complex number can be written as e to I theta, and then I just prefer to have a 2 pi there for my own purposes. So some complex number. So here comes, that's the eigenvalue. And then the key thing here is output. Well, it would be lovely if we could just get the whole eigenvalue out, but really what this algorithm does is gives us theta, and then we can work out the complex number after that. So it's not quite sort of find the eigenvalue, it's like find an important piece of information about the eigenvalue and do the rest of the computation yourself. So this is the Swiss Army knife. And I'm going to, so then as I said, it's actually more general. What I will present has the property that if you give it a superposition, a linear combination of eigenvectors, then you will get out one of the eigenvalues associated with these eigenvectors, which is really, really good. So this is where phase estimation goes from being useful to being ultra useful. And indeed, it's the generalized version of this that I will talk about today. But I'm sorry, it's the generalized version that I will use to solve my problems with Grover's algorithm. But it's this simple version that I will talk about, because it's just much easier to walk through the math when we just focus on this. So maybe I can say if you take Shor's algorithm, what does Shor's algorithm do? It factors integers. What does that mean? It means that there's some kind of probabilistic algorithm where you go into some number theory and you want to find the order of a group that one can look at. And then how are you going to find the order of the group? Well, you do phase estimation. So it's like once you get to order finding and you realize you need something smart, you do phase estimation. Another thing is if you are doing this sort of solving linear equation, so you have AX equals B, and A is a matrix and B is a vector, and you're looking for X, the first thing you do is phase estimation, and then you do something after that to wrap up. And then, as you will see later, it's like I go back to Grover's algorithm and I say, I wish I have this general case where I don't know how many needles are in the haystack, and I wish I knew theta, because then I could work out how many times I should iterate. What do? I apply phase estimation. So with that as motivation, let me sort of get going on how this algorithm works. So it turns out that we need sort of a little bit of preliminary something here. Which is, so let me, I'm going to have an n and an m. So this unitary u, this is working on n qubits. So it's just like before. So u works on n qubits. And so it means that a whole bunch of vectors you will see are n qubit vectors, so 2 to the n vectors. And then it turns out that there's also going to be an m in the story. So n qubits, but then there's also going to be an m, so that we're actually going to work with, so let me write this here. So we are overall going to work with m plus n qubits. So there's a question about what about these other m? And the idea is that those m qubits here, they are going to hold eventually theta. And so it means that we are going to get theta with a precision of m bits, I guess we could say. So here we have m qubits, right? We know that when we measure them, we can get m bits out. And so it means that eventually we will get theta with precision m. So we can say precision is m bits. So that's the idea. So we're going to do a lot of stuff with these. Okay, so now comes the preliminary thing that I want to do, which is we need to be able to do the following maneuver. It just comes up, and I want to write it out separately here. So let me just say we're going to do some iteration, and the idea is the following. So we have our matrix U that we are given from the problem, and I'm going to write this operation that is going to do something interesting here. I'm going to write it as, I'm just going to remember that this is my M. And then it's going to do something on U. So there's some kind of operation there based on U. And then here we have a K, and here we have a phi. So what is this going to be? Phi is going to be an eigenvector in the application. And then the K is going to be a representation of number of times to iterate. So iterate this many times. So this is sort of, again, a standard quantum thing that we have to represent integers as in qubits, so we can work with them. But really, it's just the integer that we are interested in. And the way this comes out is that this K just stays the way it is, and then we iterate K applications of U on this phi. So I'm not really writing the tensor products very much. Can you survive this? There's some tensor products going on here. Can put some parentheses and stuff, but there are tensor products here and there. So I may be sloppy writing them down. I want to show the case that we will need of this, which is this follows. So this is the definition, and here comes just a little calculation. So we're kind of, a little bit in contrast to when I presented Grover's algorithm, where I write the Grover's algorithm first, and then I start calculating later. Here I'm doing some preliminary steps first, and then I'll write down the algorithm for phase estimation later. So here, I want to have a product of this one, and then here Hadamard on the first m qubits there, and then just identity on the rest. And then we still have K, and then just to pick something else, I'm going to pick psi here. Why not? This is an eigenvector. So eigenvector of U. So it means that we know that it's like we're going to apply U a whole bunch of times. And so we know this eigenvector is surely going to survive quite a lot. And then we just need to see what happens at the end. So I think maybe I'm looking at a calculation here. Maybe we can just short circuit this a little bit and say, so we know that this applying Hadamard m times has a lot to do with putting something into some kind of uniform superposition. And then when we are applying U k times, it should mean that if the eigenvalue is, so what should we say the eigenvalue is? The eigenvalue is still, so let's just write the eigenvalue separately here. The eigenvalue connected to that eigenvector is still in this style, e to the 2 pi I theta. So this means that we are going to get this eigenvalue multiplied by itself k times, right? We are going to apply U k times, we're going to get this eigenvalue. So it means that we can think of this as e to the 2 pi I theta and then times k, another exponent there. So that's roughly what we'll get. So I'm just gonna write the result of this whole calculation, and then we sort of take it on faith that the constants here and there are right. So all the Hadamards will give us sort of a big thing, big 1 divided by big number in front. And then we get a linear combination of a whole bunch of cases here. And here comes this thing that I keep saying, 2 pi I theta k. Maybe I'll write it as k theta. Why not? And then k is still there. And then the eigenvector. This seems very reasonable. So the idea is that we got the eigenvalue to the k. So what we want to do in phase estimation is that we want to essentially want to take this kind of thing, and then we want to post-process it in a way so that theta shows up here. And so it means that our dream is to kind of do this. So this is something that happens in quantum algorithms all the time, that the thing you are interested in shows up in an exponent, and then what you want to do is to move it down, and so it shows up in a ket here, and then you can measure and get it. Right? So that's really what this is all about. We apply k times, we get something under control, so we have sort of a k and a k, and then at that point it turns out that's a good point to go in and do post-processing. So our post-processing is going to be here. And then we really would like this k to go away, and we have a theta instead. Okay, question. Somebody? Yes?
Was the k on the level above, is that supposed to be a 0 or is that actually supposed to be a k? Like one level above, I think it's supposed to be a 0, and then you apply the Hadamards a bunch. Yeah, that level. Is that supposed to be a k? Yeah. Do we sum over all the k's after in the next step?
It is a k. Wait. Okay. That's a good point. That should be a 0. You're absolutely right. We haven't gotten to this yet. Okay, very good. Thank you. This saves me. Yes, the m, we start in 0. This is plainly a typo on my side, but a bad one. So we start with 0, and then what happens is that Hadamard will put this into a uniform superposition. So we have all the different k's represented there. Hadamard produce a big constant there, and the rest I already explained. Yes, thank you. Now it's right. Okay, other questions or bugs or that kind of thing? Okay, so now the question is then, how do we process this stuff? And yet again, there's going to be a story here about how all of this stuff is probabilistic. So we are going to do things, we cannot be sure it's right, and things have to be repeated and so on. But we'll see what the probabilities are when we get there. Yeah, question?
Is it, should lambda have a subscript of k? Maybe that's what.
Oh, no. I hear the m is just there to signal that we are working on m
On the
qubit.
right-hand side, m just doesn't appear. Once you apply lambda m.
Yeah, but it's sort of there to say that this is m qubits that are there. So,
Or rather, k doesn't appear on the left-hand side. On the left-hand side of the equation, there is no k.
Right. Yeah, I don't know. I have always written this m, so it is possible that it's better to write a k there. So
K is a dummy variable.
Okay, sorry. Yeah, I think it's all fine.
It's okay. Yeah, I think at least to me it sort of makes sense. But okay. So here comes sort of the insight of phase estimation in terms of the algorithms part. The post-processing is done by the quantum Fourier transform. So this is like the hierarchy, right? Phase estimation is sort of what I call the packaging of the quantum Fourier transform. So right here is where we do that. So there are some questions about why exactly is that the right thing to do, and so this means I'm going to talk about the quantum Fourier transform for a while. I'm going to, as a shorthand, define omega to be e to the 2 pi I and then divided by 2 to the m. So I'm going to use this omega a whole lot. And so that's something that maybe I should just warn you. So it turns out that one can talk about the quantum Fourier transform. One can talk about, of course, the inverse quantum Fourier transform, a sort of quantum Fourier transform dagger, which is really what we need. And then there's this question, do the qubits come in this order? Do they come in this order? All of this actually really matters to get this right if you want to program this. But because we're just doing math today, I probably shouldn't say just math, but I mean, I'm interested in programming things on quantum computers, so that's what I mean. We're not going to go and implement this and see it run. So I'm going to be very loose on the order of the qubits and the this and that. But okay, so here comes the definition of the quantum Fourier transform, and I'm doing subscript of 2 to the m just to remember how big these vectors are. And the definition is as follows. There's a big constant here. And then comes summation of all the cases, 2 to the m minus 1. And then omega, so that's the omega from up there, to the j times k. So the j is this one there, and the k is this one there, and then ket k. So it's also there. Right? So that's this is the definition of the Fourier transform, really, but then I write QFT because that's what I'm going to use it for. And then the classical paper from the 1960s says that there's a really fast way of doing this on a classical computer, and then the miracle is that we can do it exponentially faster than that algorithm on a quantum computer. And I just want to make a remark, which is what we're really going to need is quantum Fourier transform dagger. Let's see if I can write a nice dagger. Because it's inverse, let me start with k. And then it's going to, I think you all know how to do the inverse of this thing, but let me just write it anyway. So here it becomes omega, and then it becomes minus. And then I switched, so here I want to sum over j. And so this means that I get k and j mixed, and here I get j. So just to sort of make it look like here I'm going from j to k's, and then here I go back from k's back to j's, right? So, but I think with a little bit of energy or knowledge, one can see that if you multiply these two out, you will get the identity function. And it's always because these omegas cancel out. So maybe I can say that we can write this as a matrix. So what does it look like if we do this as a matrix? So it turns out that it's this matrix here. So let's just do the forwards one. So QFT 2 to the m. And so, okay, we have a constant. We should not forget that. But it looks like this. First row, 1, 1, 1. It's all ones. Second row, then it becomes 1, omega squared, up to omega 2 to the m minus 1. Third row, 1 omega squared. So everything is now even more, omega to the fourth. And then we go to omega, and then it's a really big number, 2 times 2 to the m minus 1. And then the ones continue. And then the bottom row, now we have omega 2 to the m minus 1. And then omega, then it's 2 times 2 to the m minus 1. And then down here in the corner, it's so big that it's omega to 2 to the m minus 1 squared. So you can see there's kind of a pattern of multiplying by omega a lot. And so it's a really big matrix, right? So as usual, we cannot just write out this matrix and then work with it. We have to have a fast implementation. And so classically, this can be done in a very smart way. And then in quantum, what we will do is that we will actually just work with m qubits. And then it turns out that this can be done in quantum with a circuit that's not very big. And given that I'm not going to say much about it, I'll just show what the circuit is. And then we can just sort of look at roughly the size of it. So my picture of the circuit has disappeared somewhere here. It looks as follows. So it's kind of a recursive thing. So the way people normally like to do it is that they, okay, I'm going to do the inverse. So this is where it's important. The one we actually need is QFT dagger, and we're actually going to write the qubits in the opposite order that we normally do. But all things aside, the structure of it is as follows, that here we have QFT on 2 to the m, and then we have one more here. So this is where we go to twice as many elements in the vector. And then recursively, so this is like the recursive case. So here we have m plus 1. Okay, that doesn't look too good. M plus 1. And then the recursive structure is the following. So we just continue these things here, dot, dot. No, there's no dot, dot, dot. So the idea is that here we have this gate here, which is control C. So this is this matrix here, 1, 1, 1, minus 1. So that's a symmetric gate. That's why the notation here is symmetric. And then what we need to do is then to do this for every one of these. Okay, so at some point we have to do dot, dot, dot. Let me do it here. Dot, dot, dot. So we have this, and then at the very bottom, Hadamard, and then done. And the reason why I was drawing all of this is that now we can see roughly how big this circuit is. Here, clearly, we have m of these, and we have, okay, one more gate over there, and then clearly this should be like m minus 1, and then one more gate, right? So it's more or less the sum of all the integers between 1 and m. So it means that the size of this whole thing is sort of m squared. Can I get you to accept that? It's just a simple counting argument. So for what it's worth, we could now dive into, just like I did for Grover's algorithm, a correctness argument for why this thing, so it's not sort of completely correct. It's like you have to put some quotation marks, but why this thing is approximately computing this thing, give and take the order of the qubits. Okay, question?
What is the classical scaling for the FFT?
The classical thing is polynomial in 2 to the m, and it's a very low polynomial. Right? So here we are logarithmic in 2 to the m, or we could say it in a more quantum-ish way. It's polynomial in m, and then the classical one is exponential in m. Right? So you can imagine if you're thinking about this on a classical computer, it seems like a huge victory to do this in like m log m or something like that. But then, this is actually the answer. So the famous paper from 1965, Cooley and Tukey, computes this kind of thing in m log, 2 to the m times log 2 to the m. Right? And now we're going to do this in m squared. So much better. Other questions about this? So that was about as much as I want to say about the quantum Fourier transform. I want to go back and talk about phase estimation. So this means that what we are doing here is that we are taking a brilliant idea, of course, from Peter Shor, that makes this circuit here work. And then what we are doing is that we are packaging up this thing so that at the surface level we can solve this problem, which is then the one people want to solve over and over in different contexts. So I'm going to continue the phase estimation story, and I think we can go to this page here. Haha. Here comes the definition of phase estimation. So you know what? As sad as it is, we will erase the circuit and write the definition of phase estimation. So this is the actual algorithm. And so we operate on, as prescribed, a unitary matrix and one of its eigenvectors. And what we will do is the following. Actually, let me write it as psi. I've written psi often enough. Let's do that. So what this does is that it begins with m qubits that are all 0, and then psi. And then we are going to do this maneuver over here. So that's the first thing we'll do. So lambda mu, and then this Hadamard show there, Hadamard m, and then I n. And then comes the post-processing, and the post-processing is then, as advertised, something about QFT. So I will write it as, it's really QFT dagger, 2 to the m, and then we'll do nothing on the other n qubits. So that's where the post-processing is, right? So here, post-processing, at least in my terminology. So, okay, so we should see to that this works. So, so this is where it starts to be probabilistic very soon. Question? Oh, I need to write the exponent larger. Yeah, I can. Yeah, sorry. It's a, I asked for a lecture room with a lot of boards, and they gave me this. So it's like, that's a little bigger. Does it help? So there's an M and an N. What can I say? I'll try to do better in the future, but it's like, right now it's like, So, we have to take sort of some medicine here, which is that it's not going to work perfectly. So we already used to this from Grover's algorithm. This is not going to be perfect, but here it's definitely not going to be perfect. And so what I will do is that I will show a calculation for a case where it is perfect. And then we will start to look at how bad does it get if the situation is not perfect. And it turns out that we kind of have to go back to the beginning of the story and say we're looking for theta. And there are some thetas that we can find perfectly, and then there's a lot more thetas that we cannot find perfectly. So let me first focus on the perfect case. What is the perfect case? So here, good case. So this is where you know what? I'm going to move to this board here. I'm going to delete this wonderful matrix. And then I think what I will also do is I will say we don't. At this point, let's just say we don't need QFT anymore. We just need QFT dagger. That's the one we care about. So I'm going to erase and then remember to switch these guys. Maybe it's not so important. Okay, you know what? Let me just keep it this way, and then we just remember that QFT dagger is the one with one divided by here instead. And I think we are good enough. So now I will start the calculation. So we are going to focus on a good case. And the good case turns out to be one where theta is of a particular easy form. And in this case here, an easy form is j divided by 2 to the m. And so a nice j, an integer j. That's the good ones. So of course there are many of these, but there are also many thetas that are not like that. But you will see that if we do this, it's going to end well for us. So I'm going to do phase estimation on u and psi. And so I'm now saying that psi has this eigenvector theta, one of the good ones. And let's see what we get. So I'm just going to use this definition over there. So in the sort of spirit of what I've done before, I'm going to write the whole thing. So QFT dagger on, we have to remember the I to the N. And then we're getting this lambda M, U, and then comes Hadamard M. Oh, here's the exponents. Okay, keep complaining. I think I may not do this as well as I would like. So here I should remember to write tensor product N. And then finally, those two, 0 to the M, tensor product. And then here comes the eigenvector. Okay, so we have this. Now let's see what this is. So we already did a calculation on this whole first thing. So that calculation is still sitting over there. So I'll just plug that in. So we get all the way up to this point. So we get QFT dagger, 2 to the M, some stuff. And then we put in this. Okay, so 1 divided by 2 to the m divided by 2. And then a sum. And here we are doing k equal to 0. And then the whole point, 2 to the pi, 2 pi I k theta. There's the k. And then here we also have a k. And then finally the eigenvector is still sitting there. So how do we write this? and then psi. Okay, so we have that. And now the whole point is that somehow this QFT should help us out. And so the way I will organize myself around this is to say theta is one of the good guys. So this means that here we have j divided by 2 to the m. So that should be helpful. And so if we think about what this is, so we remember that omega is up here, right? So now it's beginning to look a lot like omega. So we have e to the 2 pi I, we have divided by 2 to the m, and the only thing we have left is k and j. Right? That's all there is. So it means that this whole thing is really just omega, and then I would write it as kj to write it in the same order they came in, or j or k, whatever it is. Maybe it's jk. Oh, amazing. So if we look at this carefully, that's what we have up here. That's 1 divided by 2 to the m, sum omega kj, and then k, and then, okay, the bracket ends there, right? That's the quantum Fourier transform. And so what we're doing here is we're doing inverse quantum Fourier transform. So all of this should just cancel out. So let's cancel that out, this time correctly, not with as many bugs as I've had before today. And let's see what we get. So so what does the quantum Fourier transform do? It gets us, when we do inverse, it gets us back to j. And then we still have the eigenvector sitting over there. So okay, so we got j. So if we have j, then you see, so we get this. It's exactly like the calculation for Grover's algorithm. We get something here with probability 1. It's really good. And then what do we want to do? We just measure these qubits here. So we have measure these m qubits. What do we get? We get j. And then once we have j, then it's a piece of cake to get us to theta. And then we have what we need, right? So that's the good case. So probability 1. And so what was all this for? It was for showing that when we cook up things this way, using this iterative thing that brings up k into the exponent, it's all we need to do is to apply the inverse Fourier transform, and then we get that something important about that theta moved down here to the position where k was, and then we're good. So that's pretty much that, except that then there are all the other thetas. And so this is where the story gets probabilistic. So we kind of don't know what theta is, right? We want to know theta. So we don't know in advance whether this is one of the good thetas or one of the other thetas. I'm not going to call them bad in this case. It's just another one. And so we have to be prepared for that it may not be one of these. Question?
To clarify, lambda and u is just a quantum Fourier transform, then we do the inverse quantum Fourier transform?
So are you pointing over here or over here?
Over there.
Okay.
What is the definition of lambda, maybe?
This is the definition of lambda. So it's just a way of saying this line is the definition of lambda. Okay, so it's saying that you start with a u, and then what we're going to do it is like this thing that's defined in terms of u, and the way it's defined is over here. So it's a.
But it seems from the third line that it does a quantum Fourier transform, a non-inverse quantum Fourier transform.
So we're going to do post-processing by the inverse. So the thing is that this maneuver here produces something that looks a lot like the result of the quantum Fourier transform. And then we do inverse to get us back. So I think that it's much better to write quantum Fourier transform inverse here, and then it matches up with what I said over there. So I think so maybe that's sort of a high-level way of saying this, which is that we have this u, and then when we apply it a number of times, we just end up in a situation that looks a lot like it was produced by the quantum Fourier transform. And then it's like, okay, great, let's do inverse quantum Fourier transform. And then it just happens that we get back to a situation that has exactly what we need here. Right? Or, for me, the more poetic way of saying that is that we manage to get this something important about this theta move down here where we can measure it. Okay, so now comes sort of the moment of truth in the whole lecture here. Okay, maybe not yet. Question?
Sorry, maybe to just be really explicit, could you write out what lambda m of u for like k is 0 and k is 1 and k equals 1?
Oh, but yeah, of course. So let's do lambda m of u for 1. So here comes 1, and then tensor product u to the 1. Right? That's really all that's going on here. So this is why, this thing of writing this thing here, this means that it's meaningful if this is what it was, that we would end up with a 1 over here or something like that. It's really just a bit encoding of a number. In this case, it's kind of decimal, I think. It's a decimal expansion, but with bits. So it's not decimal expansion, it's bit expansion of the whatever comes after the 0 dot. So yeah, okay, so now comes the moment of truth. So we need to accept that this only works well for theta. And what we really need to take an interest in is how successful are we going to be to get like a j here if theta is one of the other ones. And so it means that the next part of the lecture is all about getting to know about the probability that this will work out for us. And so that probability, yeah, well, we'll see what it is, but it will take some calculation to get there. Any further questions before I dive into this? So I need to take a look at my boards, and I think that we're finally at the point where this board here. So apparently now I realize that is that a whiteboard? No, it's not a whiteboard. It's just a. I think there are more blackboards behind, but then there's some padding to. So what I will do is that I will delete all this, sad as it is. And let me tell you the general case. So if we do phase estimation on u and psi, and we don't get to use this observation here, but we just get all this. The general case is as follows. So after some messing around with the inverse Fourier transform and all this stuff, we get the following. So here comes 1 divided by 2 to the m, another summation, k this time, also a big summation, and then omega, same omega as before, and then here it's k, and it's kind of crazy. So 2 to the m theta minus j, and then finally at the end of all this comes j and psi. Okay, so there it is. So this is just doing the calculation like before and canceling out with the quantum Fourier transform inverse at the right time, and this should be correct. So now we can take up an interest in getting j. So I'm writing it this way because so now we can focus on a particular j. So of course the summation variable here is j, but let's think of a particular j and then ask ourselves, what's the probability of getting j? So over here, that probability is 1, right? Over here, we have to take up an interest in norm squared of this thing here. So that is going to lead to quite a lot of calculation here. So I'm going to think of the probability of getting j. So now I'm really thinking about a particular j as, so I'm going to call it pj, because I will need an abbreviation for this. So it's going to be norm squared of this. So let me write this out. So 1 divided by 2 to the m summation k equal to 0, big summation, and then omega k, and then a whole bunch of stuff here. 2 to the m theta minus j, and then norm squared Okay, so this looks pretty scary. I just want to know something about PJ. What I really want to know is the lower bound on PJ. And so that's my quest here the next sometime. Question.
In the first line, the left-hand side, where is the first qubit? Like the number of qubit doesn't match to me.
So did I mess something up? Okay, so where are you in the...
Like on the left side, so it needs some ancillary qubit. The first line.
Here?
Yeah. Does it need extra?
No. So we don't need extra qubits. So, okay, very good, yes. So the thing is that I've short-circuited the thing is that, yeah, so it could be that my notation is maybe not the best. So here I'm just introducing these extra qubits here, and I'm not really saying, so it's like phase estimation is quietly introducing the m extra qubits, and then we end up getting this. Right? So it means that, I think this is more like a computer science way of saying it, is that the m qubits, they get introduced as something along the way. But of course, if we want to implement this as a unitary, then we absolutely need to bring in m qubits from the beginning. So I will leave this implicit. I think this is more like how I think about it. But internally, of course, there has to be m qubits that are initialized to 0 at some point. Okay, other bug plots like this. So otherwise, I am going to cook a lot of soup on this scary-looking thing, and what I want is a lower bound on what it is. And the lower bound, I mean, first of all, I need a non-zero lower bound. Otherwise, I have no confidence in this whole project. And I would like this lower bound to not be too bad. So, more than a little bit. So the reason I'm showing you this is that, to me, the following development is like an interesting case of how one can take something and just messing around with a little bit and then actually put bounds on these probabilities that happen in quantum computing. And so I think that for people like you who maybe already or will be developing quantum algorithms, this is the kind of reasoning that comes in sooner or later in your life. So I'm just going to give the example of the phase estimation reasoning because it's a famous one. Let me just put this constant outside. 1 divided by, I guess we'll just here write 2m, and then this thing is then just slightly smaller. So 2 to the m minus 1, and then still have this crazy stuff. 2m theta minus j, and then norm squared. Okay, here we go. So put a bound on that. That's the goal. This looks an awful lot like a geometric series, right? Because it is. So we're going to use the formula for geometric series. So I'm sure you remember that it's something like a fraction of 1 minus the exponent that's 1 bigger than the highest one divided by 1 minus and then something with just the case of k equal to 1. So I'm going to write that here. So we get we still have this constant sitting out there, and then so we have 1 minus, and then so the case at the bottom should just be k equal to 1. So we get omega to the 2m theta minus j. And then in the exponent, we should use the highest k we can get. So we get like a 2m there somewhere. So I'm just thinking about how I want to write this. Maybe I'll put the 2m outside. So how about I write this so it looks a lot like this, 2 to the m theta minus j, and we'll put big brackets here and write the 2 to the m out there. So 2 to the m, 1 higher than this, right? That seems like the formula for the geometric series. And anything else we can do here? Let me just see if there's any smart maneuvers that seems to be worth applying. Seems quite good to me. So maybe the only thing that's worth doing is that we can sort of decide whether it's more profitable to write 1 minus this or this minus this, right? But we're doing absolute value here, so it's like, yeah, it'll probably be fine. So actually, I think for my own purposes, I'll move it over. Why not? So 2m, and then norm squared. Maybe how about we split it up? So that's one thing we can do productively here. We'll split up into two cases here, norm squared, norm squared. So we get omega 2 to the m theta minus j, 2 to the m minus 1, and then omega 2 to the m theta minus j, and then minus 1. Okay, so now at least we have some things. What I want to do here is I want to start to think about the numerator and the denominator separately to be able to make progress on this. And then I will show the case of what I can do for one of them, and then I will state what one can do if you continue and do something for the other one. So I'm now going to backpedal over here to the good case of theta being one of these. And then I'm going to take up an interest in the case where theta is just like epsilon off of one of the good ones. So it's like you draw like a little circle around the good ones, and then let's look at that. So we're not going to make it too hard for ourselves. So somewhere here, I'm going to define an epsilon, and I will just say epsilon could be positive or negative, but it's going to be really, really small. It's going to be 1 divided by 2 to the m plus 1. And so it means that it's again very much this thing of saying that it has a lot to do with m bits of precision, is what I want to say. When we measure, we are going to get something that is going to be very, very close to the one we're interested in, which means that the first m bits of the j we're going to measure are going to be good. And now the only question is, with what probability are we going to get that if theta is one of those? So I'm going to say that, to make it very explicit, theta is equal to j divided by 2 to the m, like it was before, plus epsilon. And then this should really be mod 1. So theta is very, very close to a good one. Okay, so that's our ambition level here. And the question is, in that case, for all of those thetas, what can we expect for pj? What's the probability that we will measure that when we run this thing? And so this is where I will say, let's decide that this fellow here, so I want to write this as, let me sort of very concretely write this as, okay. So now I'm trying to short circuit the notation. I'm not quite convinced that this will end well for me. So let me actually write over here what I want some abbreviations to be. Again, I want an A and a B. Going to be quite different from Grover's algorithm, but here they are. So I want the first one to be omega 2 to the m epsilon minus 1. And then I want B to be just omega 2 to the m epsilon minus 1. Okay, so those two things there. Those two I'm going to look at a lot. So now the question is, how is that related to this stuff up there? And so by doing a little bit of messing around with all these exponents, which I think I've sort of decided that this is just error prone. If you look at this for a few minutes, you will see that this is now equal to, written in terms of A and B, as 1 divided by 2 to the 2m multiplied by a squared divided by b squared. Kind of, I think it, doesn't it look, so this is where one has to look at that this epsilon is defined in terms of this 1 divided by 2 to the m something, and then theta is defined in terms of epsilon. So if you look at these two and then bring that in, then you should end up with this thing here at the end. So let me take that on faith and move on. So now, to be able to, but the goal here is still that I want a lower bound on pj. If I'm going to have a lower bound on pj, the best would be if I could get a, well, it would be nice to get a bound on A and a bound on B, right? So, so what should we shoot for here? Just Okay, so let me just give the case of A. So I just want to hand wave my way through why we can put a lower bound on A, and then of course if we could then also get an upper bound on B, then we could mush these together and we get a lower bound on P, Pj. So any questions about this before I say something about these bounds? So So what is this A? So A is this. So what can we say more about this A? So actually there are different ways of writing this A. Maybe I will need another way of writing A. That's quite nice. I'm going to write A written out in terms of epsilon. So A can also be written as e to the 2 pi I, 2 to the m, epsilon. I think this is quite unsurprising when we look at what we have there, and then minus 1. Okay, so let me look at, so I'm bringing in what omega is, and then
So in the first line over there, is it 2 raised to 2 raised to m? On the left? Is it omega?
Yeah, so this is what I had. It's a 2 to the 2m. So it's a
It's 2m. It's not 2 raised to 2 raised to m.
2 to the 2m, yes. So
2 raised to 2 is to m.
yeah, yes it is. Yes it is. Hmm?
Yeah.
So it's just sitting there. So it's like, it's just like that. So epsilon is an exponent, of course, of omega. Okay, I'm quite sure my calculation is correct. So if you don't mind, let me show my argument for what's going on. I think that maybe this epsilon at the end, that I don't know whether it's strictly necessary to, there should maybe be absolute value around the epsilons. Let me not be too worried about that. Now I just want to give an estimate of what this is. So again, we know that this is e to the I and then some kind of whole bunch of stuff. So this is a complex number. And 1 we can think of as a complex number as well. And so, and we know that not only is this a complex number, but e to the I something, it's a complex number with norm 1. Right? So it means that we should be able to think about it this way. So over here, okay, so we have some kind of unit circle here. And then over there we have 1. So that's very literally this 1 that's sitting there. And then we have this thing is sitting like over here somewhere. So here is, this thing is like this. So that's this number there. And then, of course, we can take up an interest in what is then the arc length of this. So that should be everything else that's not e to the I. So it should be something like this arc length there is, so here. So the arc length that we're looking at is something like 2 pi, 2 to the m, okay, epsilon. We'll just keep writing absolute value. I think that's kind of what it is. Yeah, I have notes on this. I want to see if I got the same when I did the calculation over here. That does seem like that is the arc length. So that's just like saying what is this distance here. Okay, so that's a distance. So the next thing we can take up an interest in is that what this thing is really saying is that it's talking about this distance here. So then one could say, okay, so what is the relationship between the arc length and this distance? Is there anything we can say about the relationship between these two? So it's definitely true that the arc is longer, right? The question is there a bound on how much longer? Is there anyone who has an opinion about how the ratio between the arc length divided by, so of course this distance here is quite literally a, right? So we could say arc length divided by a. Is there any way, so this is equal to this, and a is a, is there any bound we can give on how big it can be? Does anyone know anything about this? Pi over 2. Pi over 2, right? So it's like, it's like over here, this whole thing should be right around pi, and then this distance here should be 2, right? So there's like, it can go all the way up to pi over 2, but then otherwise it's smaller than that. So this is bounded by pi divided by 2. Okay, so then here we have it. We just have a whole bunch of stuff. Of course, we chose epsilon, and so we already have a definition for epsilon. And so then we can work out something about A. And it turns out that if you do math on this long enough, we end up here that A is bounded from below by 4 epsilon 2 to the m. So again, this can be checked, but this is just taking this thing over there and then organizing it over there. So we got a lower bound on A. And then similarly, one can get an upper bound on B. And then if you then put these two close together, then what we end up with is that, there's no place to write it other than here, is that we get that 0.4 is a bound on Pj. So I'm going to skip the argument for B and just say that the probability of measuring J if theta is kind of within earshot of one of the good thetas is at least 40%. And so that's not bad. So it means that the way phase estimation works is that you have to run the circuit a bunch of times, and then you measure the first m qubits, and then now what you're getting is theta with m bits precision with probability at least 40%. Assuming that this is something, assuming that theta is one of the good ones. If it's further outside, so you can imagine now what we have done is we have drawn a whole bunch of circles around the good cases, but there are still things outside, depending on how big epsilon is. And then one can continue the story and then do more math on it and talk more about what are the bounds and getting something good for the other cases. But the message here is that a lot of the time, one can succeed with probability at least 40%, which is good enough in practice. And so that's really what phase estimation does. It allows us to run and with a good probability get essentially the eigenvalue out for a given eigenvector. So that's sort of roughly what I want to say about phase estimation. What time is it nowadays? 11:41. Okay, so I can. So any sort of lingering questions about phase estimation? Otherwise, what I want to do last is that I want to put Grover's algorithm and phase estimation together and show how Grover's algorithm solves the problem with how phase estimation solves the problem with Grover's algorithm, which is this thing of how many times should we actually iterate if we don't know anything about the database. Okay, so let me go back to. So now I erased the problem statement. But as you recall, I say that phase estimation is actually more powerful than I have been calculating my way through here. It allows you to give a linear combination of eigenvectors, and you will get one of the eigenvalues. The reason you get one of the eigenvalues is because of measurement. It's like you measure and you get one of them. But they are kind of there if you do enough math on it and see what the state is. And so it means that if we happen to have a linear combination of eigenvectors, we can rely on getting one of their eigenvalues. That's exactly what Shor's algorithm does. Shor's algorithm is not just doing the basic version where you give a single eigenvector. It's essential that because in Shor's algorithm, you don't have any eigenvectors of what you are looking at. It's like you have a very nice unitary and you have no eigenvectors. But what you have is a linear combination of those eigenvectors. And then it's like, oh, great. And then you run, you get one of the eigenvalues, you run again and again and again. You get a lot of eigenvalues, probably different ones, because there are many eigenvectors involved. And then you piece together what you found, and eventually you can factor your integer. So here we're going to do something like that, but much simpler. Instead of having lots of unknown eigenvectors and lots of unknown eigenvalues, it's a much smaller scale. So I'm going to rewind, and I'm going to go back to this thing over here. And so just to summarize where we were, we have this understanding that in Grover's algorithm we are rotating with 2 theta at a time. And if only we knew theta, we could work out how many times we should rotate to get close to the y-axis. So what about it, right? How do we get this theta? So this is where I think, okay, we'll delete this. So here comes the story about how we find theta. So I would teed it up so that I'm just going to apply phase estimation to something and out comes theta, and then I can plug in and get the number of iterations, right? So we have to like look at it a little bit to make this work. And so it goes like this. So we go back and look at our rotation matrix. So I'm going to write it the way I normally like to do it. So cosine on the diagonal, and then we have, I think, a minus sign up there and a sign here. There's a whole lot of thetas there. That's the theta we want to know. Okay, so the natural question is to ask, does anyone know what the eigenvalues are of this matrix? So I can say for myself that I, of course, learned about rotation matrices as an undergraduate, and we did a lot of linear algebra. I had 2 years of linear algebra as an undergraduate. Really seriously, 2 full years. And I never thought about what the eigenvalue of this matrix was. So maybe I tell you. So the eigenvalues are, okay, so have somebody worked it out? Very good. There they are. So of course, this is a unitary matrix, so we know there are 2 eigenvalues, and there they are, e to the I theta and e to the minus I theta. Do you want to see the calculation? It's just messing around with sine and cosine, right? There it is. So this is great news, because now we don't exactly have this matrix, of course. We have this is just the 2 by 2, but what we have is the whole body of Grover's algorithm, right? So we have that thing, and we know that it's really just going around in a 2-dimensional space. So it means that this thing here has eigenvalues e to the I theta and e to the minus I theta. It's like, great. Now it's really teed up. Now all we need to do is to plug in phase estimation, and out will come an eigenvalue. And it doesn't matter which one it is. We will be able to work out theta at the end. If there's any doubt about which one it is, we can always like run it a few times until we have both, and eventually we will get k, right? That's clear. Question? Yeah, that's true. So there was something, so that I think that this is a very good point, that that G is rotating twice. So it's probably like this. Thank you. That's very accurate. This is exactly what it is. So this sort of the overall thinking about it still stands. We have some stuff. If we can just get to one of these, we can definitely get to theta. It's actually even better, because phase estimation is kind of going to give us like theta, more or less, right? A plus minus a constant there. So it's perfect. We're just going to get theta, and we are done. We can work out what to do in Grover's algorithm. What is the problem? The problem is that phase estimation says we need a unitary and an eigenvector, and we don't have an eigenvector. So clearly, right, we don't have an eigenvector. So what are the eigenvectors actually? So I mean, if anyone is interested, the eigenvectors are something like I1 and minus I1, and that's just in the simple case. I mean, who knows what the eigenvectors of this really is, right? We have no idea. So that's like a setback. And so now the last thing of the whole lecture is to overcome this setback, and then we're done. So what is it that we have worked out eventually? So we worked out that if we start in the sort of the original Hadamard n times 0 to the n. So what was that? So we're already in the 2-dimensional space at this point, right? So sort of details aside, it's something times A plus something times B. So we're already in this space at this point. Okay, so what do we know about this? So we know that Grover's algorithm on this AB space, it's, what should we call this, invariant on this space, right? It's like, that's what we have been talking about all the time, that G is just messing around in this span of A and B. So if that's the case, then we can look at the eigenvectors of G, and then clearly there must be two eigenvectors of G that span this space. They don't have to be A and B at all, right? But there must be two eigenvectors that span this. So all of this to conclude that G has two eigenvectors that span this span of A and B. Right? So that must be true. If that is true, that's great, because here I have the initial, sort of the after initialization. All I do is I take my n qubits and I run Hadamard on all of them, and now I have a linear combination of two eigenvectors, right? I get this, which is then in the span of two eigenvectors. So I have exactly what I need. I have a span of two, I have an element that's in the span of two eigenvectors. I have a linear combination of two eigenvectors. I run phase estimation, and out comes one of the two eigenvalues, which means out comes one of these two, and I'm done. Right? So it means that this whole maneuver of showing that the body of Grover's algorithm is invariant on this two-dimensional space is helpful for two reasons. One was just to get the algorithm going, but then it turns out it's also helpful for this understanding of that we can plug in phase estimation, and we get what we need. So anyway, so that's my presentation. So let me just summarize a little bit. So in and out of the presentation, I've been talking about how phase estimation is useful for different things. You just saw one here. It seems very natural. It's very easy once all the properties are lined up. It's useful in many cases, and it's particularly useful because it has this powerful property that if you give it a linear combination of eigenvectors, you get one of the eigenvalues. And then, so I talked about Grover's algorithm. I talked about that it's kind of easy if you're looking for a single thing, but if you don't know how many needles that there are in the haystack, then you can always do this. And then you can work out what you need to do, how many times to iterate. And so I'm hoping that you're all going to develop a lot more new quantum algorithms, and I feel confident that sooner or later you're going to need phase estimation in there somewhere. Thank you.